Our topic is gravitation, gravitational forces. Now let's have a context to this study. There are basically 4 types of basic forces in nature, and because of these forces we have 4 basic types of interaction between particles in this nature. The first is gravitation or gravitational force or gravitational interactions. Gravitational interactions. This is amongst all these 4 types, this is the weakest type of interaction or force, the weakest force. But this weak force results in all these planetary motions and holding this galaxy and all this universe. This is responsible, or this is credited for holding this whole planetary system, like our this sun. Then we have several planets revolving around the sun. Then we have galaxies and this whole universe. This gravitational force actually keeps them at the points or places where they are. Second type of interactions are called electromagnetic interactions. What are these? These are the interactions between electrons and in an atom, then atom in molecules, then molecules in forming a crystal. So these types of forces result in interactions between particles like electrons in an atom and so on. And these account for phenomena such as friction. Then you have refractive index, you have viscosity. So these types of properties that you see in nature, friction, refractive index, viscosity, all these types of properties, they are because of electromagnetic interactions. Okay. Then the third type of interactions or force are called strong forces. Now we are talking of forces, the last 2 forces that actually occur between or within atom. So this is strong forces or strong interactions. This is the strongest of all these types. This is the weakest, this is the strongest. What are they responsible for? They bind nucleons. That is protons and neutrons, positively charged protons and neutrons in a nucleus. So they are very strong forces. They bind the protons and neutrons and other particles in the nucleus, and you know that has to be stable. If that was not stable, probably this universe wouldn't have existed. So these are the strongest type of force, but they occur or they exist at very small distances of the range of 10 to the power minus 5, minus 7, minus 9. So these are very strong forces but act for very small distances. And the last one is weak forces. What are these weak forces? These are the forces, these are the forces that exist between very light fundamental particles, like you have muons, neutrinos, leptons. So the forces acting between them, these forces act between them. Okay. So these are the 4 basic types of forces. We are interested in studying gravitation for now. What is gravitation? Let's start our course on gravitation. We'll start with Newton's law on gravitation or of gravitation. It was given in 1687. So what is Newton's law of gravitation? It states that every particle of matter in the universe attracts every other particle of this universe, and the force of attraction is directly proportional to the product of the 2 masses and is inversely proportional to the distance between them. If r is the distance, it is inversely proportional to 1 by r square, and it is directly proportional to the product of the 2 masses. If we have 2 particles m1 and m2 and the distance between them is r, then the force of attraction between them, and this is not repulsion. In electrostatics you have repulsive as well as attractive forces. When the charges are of same polarity, they repel, but opposite polarity charges attract. But here the force is attractive only. That is, every two particles, each, if we have two particles, they'll attract each other because of this force, which is directly proportional to the product of the masses and inversely proportional to the distance between them. Therefore, you know how we handle proportionality. We multiply it with a constant. So that constant, as per Newton's law of gravitation, is given as G, which is called Universal Gravitation Constant, and its value is, you know these things, 6.687 into 10 to the power minus 11 Newton meter square per kg square. Okay, so this is Newton's law of gravitation. Clear? Then, if this is Earth, it attracts every particle towards its center. This is called, this, if the mass of this particle is m, it has an acceleration due to gravity. We have a term acceleration due to gravity, which is given as g, small g, 9.98 meter per second square. So the force towards this will be m into g, this you know, which is called weight. Okay, now let's calculate the density of Earth. Okay, what is the density of Earth from this Newton's law of gravitation? We know we have this mg, but we also know this is the force that is attracting a particle towards the center of Earth. Now we know this is equal to, from Newton's law of gravitation, this is equal to g, let me be the mass of the Earth. Now small m is the mass of this particle by distance, this r. So we are talking of small distance from Earth. This is Earth, so maybe 1 meter, 2 meter or 100 meters from Earth. So that will be almost equal to this r, which is the radius of the Earth. Okay, so this is from Newton's law of gravitation, and mg we know, m into acceleration, that is the force acting towards the center of the Earth. Now this cancels. From here we get an expression for acceleration due to gravity, which is g into me into r square, where g is universal gravitation constant, me is the mass of the Earth, and r square, r is the radius of the Earth. So if we have these values, we can find g, or if we know what g is, because we can see, we can calculate the force that is acting on a particle of mass m, from there we can get g. So if we have g, we can have these values. Okay, if we have g, we have r and g, we can find me. So this is the expression for g. I'm writing it here, g me r square. Now considering Earth to be a sphere, you know the volume of this sphere is 4 by 3 pi r cube. Volume of a sphere is this, since r is capital R here, so we can say volume is this. We are interested in finding the density of the Earth. Density of Earth, let's write it like this, rho. So what is density? Density is mass by volume. Okay, what is mass? From here we can write mass is, this is the mass of Earth, see, me, that is gr square by capital G. Okay, this is mass of the Earth, gr square by capital G, by volume. Volume we have seen 4 by 3 pi r cube. Now r cube, so this cancels this. So what we get? We get 3g, 3 goes to this side, so 3g by pi r capital G. See, so the density of Earth is this. We have forgot one thing, this is 4. See, 3 goes up and denominator we have 4. So this is 3g by 4 pi rg. You should remember this expression and this expression. You will need it. Where in questions you will be given one or two value of one or two variables, and you will ask to find the value of the other variable. So you should keep this in mind. Sometimes we require to do some correction to this. And what is that correction? We have taken Earth to be a perfect sphere, so that the volume is 4 by 3 pi r cube. But in actual, Earth is spheroid, not exactly a sphere. What is the meaning? The meaning is that this equatorial radius, this one, let this equatorial radius be r1. Then this and this polar, this is polar radius. So polar radius and equatorial radius, if they were equal, if they would have been equal, it was a perfect square, but they are not equal. So if equatorial radius is r1 and polar radius is r2, this is actually given as 4 by 3 pi r1 square into r2. This is a more, closer approximation of the volume than 4 by 3 pi r cube, considering r to be the radius of a homogeneous sphere. So we use this expression for volume, and we have rho. If we know what is the density, then we know this, so that we are able to, I'm rubbing this. So what we do, if we know the density of the earth, we are able to find the mass of earth. How? We know this volume and we know rho. Rho is there and this volume. So that this will be 4 by 3 pi rho r1 square into r2. So from here we get the mass of earth, which is more accurate than the first expression. Okay. So similar to these deductions, we can find the mass of the sun also. How? In similar pattern. Let's say this is your sun, and this is the orbit of earth. Let's say this is earth. When this is revolving around the sun, it will experience a centripetal acceleration, that is centrifugal to this side. And what will be the value? The value of centrifugal force will be mr, if m is the mass of earth. So me is the mass of earth, then me r omega square, or me v square by r, where r is this distance, the radius of the orbit. This you know. Why? Because v is r omega. What is omega? Omega is angular frequency and v is the velocity of the velocity of earth on this orbit. Omega is the angular frequency. Okay. So this is the centrifugal force. It will be balanced by which force? Gravitational force. That is the force acting between these two bodies, sun and earth. So this will be in this direction and centrifugal force in this direction. So this will balance. This will be equal to G ms me by r square, where ms is the mass of the sun, me is the mass of the earth, and r is the distance between the two. So this expression is important. From here you can have. So if you want to see what is the mass of the sun from these expressions, let's say this one and this one, me cancels, r square goes to this side, so it becomes r cube omega square by this g. So this is the expression for mass of the sun. So see, it is so easy to find the mass of the sun from here. We know what is g, the universal gravitational constant. We know the radius, sun's center to earth center, and we know omega. What is omega? From this expression, we know omega is ms into g by r cube. But we know omega is the angular frequency. Angular frequency, this means it is 2 pi by t, or t is equal to 2 pi by omega. This is the time period. We know it takes 365 days to have a complete revolution. So it is 365 days into 24 hours into 60 minutes into 60 seconds. So from here we know omega. So if you put the values, you'll get the value of omega. And you put the value here, you get the value of ms, mass of sun. So you know r, you know g, you know omega. You'll put every value here and find the value of mass of the sun. Okay. So from here we have a very important expression or relation. See, omega square is equal to ms into g by r cube. Okay. But, or you can say that omega square is inversely proportional to r cube. But omega is inversely proportional to t. So when omega is inversely proportional to t, you can say t square is directly proportional to r cube. You can put this by 1 by t. So we have a very important relation. T square is proportional to r cube. We'll have further understanding of this particular expression, but for the time being, it helps in finding, time period of other planets. For example, if we know that the time period of Earth is t, that is, we know 365 days, and let's say some planet X, we have to find out what is Tx. When this is for Earth, it is Re, and for this planet, if Rx is 50 times of this Earth, that is, this is R, so 50 times of this, we have a planet which is 50 times of this R. What will be the time period then? So it is very easy to find by this relation. T square is proportional to R cube. So this means Tx by TE square Rx by Re cube. Now this is, as we have expressed here, this is 50 Re. So this will be 50 cube. Therefore, Tx will be what? Tx will be Te square into 50 cube root over, or you can say Tx is Te into 53 by 2. So this will be 50 cube, that is 50 to the power 3 by 2 into time period of Earth. You will get this. So this helps in finding the time periods of different planets. The question is, there are two particles. One is of 19 kgs and another is 150 kg. The distance between these two is 0.28 meters. And it says the force of attraction between these two bodies, it is equal to that of a 0.25 milligram object. So this is mass. Force will be this into gravitational constant, that is 9.8, and milli will have to convert to kilo. So milli is 10 to the power minus 6 kilos. So from here we get this in newtons. Try to understand. The question says the force of attraction between these two bodies is equal to the weight of a 0.25 milligram object. So 0.25 milligram object weight will be this. So 0.25 in kilograms means this, and g is 9.8 meters per second square. So this is the force which is acting between these two particles. From here we have to find gravitational constant g. Let's see. So you know this is the force. This will be equal to what? G m1 m2 by r square. So we have to find this g. So g into m1 m2, that is 19 into 150 by r square, that is 0.28 square. This will be equal to this force, 0.25 into 9.8 into 10 to the power minus 6. So g will be 0.25 into 9.8 into 10 to the power minus 6 into 0.28 square by 19 into 150. Okay, so let's calculate it. So it comes to 6.74 into 10 to the power minus 5, and we have 6 here. So 10 to the power minus 11. Okay, and this will be, the unit will be, what will be the unit? This is force. So this is force. So we'll have N. This is meter square. So meter square by kg square. So Newton meter square kg square. Okay. Our next question is, the mass of the sun is given 2 into 10 to the power 30 kg. The distance between sun and earth r is 1.5 into 10 to the power 11 meters. And time period, you know, earth revolution around the sun is 365.3 days. We have to find this universal gravitational constant g. How will find? You know this g ms me by r square. This was equal to m of earth into r into omega square. This we have seen and we have deduced the expression. So this will be equal to, g will be equal to r cube, this and this, by omega square by ms. Okay, so this is the expression for g. Now g is, I'm writing it here, g is r cube omega square by ms. Now what is omega? Omega is 2 pi by t. We have to find it in seconds. This is 2 pi by t, 365.3 days into 24 hours, then into 60 minutes into 60 seconds. So what is this value? This value will be, let's calculate out, 365. So it comes to 1.99 into 10 to the power minus 7. Okay, so we'll put this value there. This is equal to, I'm rubbing this now, r cube. R is 1.5 cube into 10 to the power 11. So this will become 10 to the power 33 into this square. So 1.99 square into 10 to the power minus 14. This is square by ms. Ms is given 2 into 10 to the power 30. So What is the value? Let's see. 1.5 cube. It is 3.375 into 1.99 square. You can do it directly also. Okay, by 2. And here we have 10 to the power, see, 33 minus 30. So that will be 3 and this. So this will be minus 11. And what is this value? Let's see. So it comes to 6.68 into 10 to the power minus 11. Again, this is Newton meter square per kg square. Okay. This is a good question. It says, let's say this is Earth and its radius is RE, which is equal to 6 into 10 to the power 6 meters, average radius. A satellite is revolving around Earth. Let the height of this satellite from the surface of the Earth is small r. This is 200 kilometers. Okay. It says the time period for one revolution is 90 minutes. We have to find the density of the Earth. Now, initially you'll think, how can we find the density? Let's start. Again, this is circular motion, assumed to be circular motion. So G into mass of Earth into mass of this satellite by the distance of this between these two. So we'll have distance from here to here. Let's say that is R, which is R is what? RE plus smaller. From here to here it is RE and then smaller. So G ME MS by R square, this will be equal to MS into this length R into omega square. Okay. So MS cancels. What do we get? We get, see, G into ME, mass of Earth, here this is equal to R cube into omega square. G is given. We have to find the density of the Earth. Density of the Earth will be mass by volume. So what we need to know is mass of Earth from here. Then we'll go to density. So what is the mass of Earth? Just this will be equal to by G. So this is R. R is what? 6 into 10 to the power 6, and this is what? 200 kilometers. So 2 into 10 to the power 2 and 3. So 10 to the power 5 meters. We can write it like this. Or in this term, we can write 0.2 into 10 to the power 6, 0.2 into 10 to the power 6 meters. 200 kilometers will be 10 to the power 3, 10 to the power 5, so 0.22. So R is basically 6.2 into 10 to the power 6 meters. So 6.2 into, this is cube, we'll write 10 at one place. So cube, so this will be 10 to the power 18 into omega square. Omega is what? We'll have to find the value of omega also. Omega is basically 2 pi by t, and this is 2 pi by t is 90 minutes. So 90 into 60 in seconds. So what is the value? 90 into 60. So it comes to 1.16 into 10 to the power minus 3. So this is 1.16 square into 10 to the power minus 3. So this will be minus 6. Okay. And then we have G. G is 6.66 into 10 to the power minus 11. So here it will go plus 11. Okay. So what is the value? Let's find out. This will be, so it comes to 48.15 into, this is, see, 18 minus 6 will be 12. So this will be 10 to the power 23. For the time being, let's say this is our this. Now we have to find density. Density is basically mass by volume, that is 4 by 3 pi r cube. Now see the difference. Here we have R, that is this RE plus R, whereas here we'll have only RE, the radius of the Earth. So we'll have this 48.15 into 10 to the power 23 by 4 by 3, that is 4, here we multiply by 3, pi into RE. R is basically 6 cube, that is 6 cube into 10 to the power 18. So let's find out the value. So if you do this, this comes to this value. So if we use this 100, we multiply this by 100. So we'll get 5.32 into 10 to the power 3. And this is density. So we'll have kg by volume, that is mass, meter cube. So the density of Earth is 5.32 into 10 to the power 3 kilogram per meter cube from this expression, this example. Okay.